Hello, today we'll be discussing rotating disk. This is an important item issue in mechanical engineering because there are many mm, rotating machinery that we have to deal with, and it is important that we know the stress distribution within them. One of the very good example of rotating disk is our very own turbine disk. I'll show you some of the turbine disk. Uh, this is an aircraft gas turbine rotor. This is a steam turbine rotor. This is again a gas turbine rotor. And this is my own rotor. This a rotor mounted on a shaft, and the shaft is held on two bearings, radial bearings. So this is a typical picture that there are many examples of rotating disk in engineering, and in many cases we need to know the stress distribution. Of course, one important thing that we need to do now, but we'll do it later, that is most of these rotors may be at high temperature. So the typical elasticity solution have to be modified. But for the time being, we'll simply do it at the room temperature, and later on, if time permits, we'll look at the thermoelasticity. Okay, so we go ahead to find out the stress distribution in the rotating disk. As we discussed earlier, in earlier lectures, that the um, the beginning of the stress distribution analysis starts in the equations of equilibrium that we developed in cylindrical polar coordinates that I have shown here on the right hand side. And we also discussed earlier that for rotating disk, we can assume a plane stress condition. And if we remember, the plane stress condition gives the stresses in one of the directions, say the z direction, will be 0. So here sigma z0, tau rz0, tau theta z0. And also in addition, if we consider the symmetry of this, that will lead us to tau r theta 0. So all in combined, if we apply it to the equations of equilibrium on the right hand side, we'll see that only the first and the fourth term of the first equation will remain, others will vanish. We discussed this earlier, so I'm not going to waste time on that. So the equations of equilibrium will give del sigma r by del first term, and the fourth term del sigma, no, that is also 0, sigma r minus sigma theta by r equal to 0. But here I have added a body force term. Usually the equations shown in the right hand side ignores the body force, and it is in the static equilibrium. That's why the right hand side is 0. But here I use a body force term, which is the centrifugal force in this case, to so that we can use this equation for rotating disk. As you can imagine, in rotating disk, there will be a centrifugal force, and that will, of course, modify the stress distribution or add to the stress distribution. So we add a body force term, rho omega square, which is the centrifugal force per unit volume. Centrifugal force is m omega square r. So I take the volume out, I put rho omega square r, and this equation of equilibrium reduced to del sigma r by del r plus sigma r minus sigma theta by r plus rho omega square r equal to 0. So this is equation 1. This we have discussed earlier. This is just for completion. Now we go ahead with the solution. Now earlier when we saw the equation, we assumed we started with an assumed solution, and that was a homogeneous equation because the right hand side was 0. A differential equation like this of form, this becomes a non-homogeneous equation because the right hand side is not 0. So we have to have a particular solution added to the homogeneous solution. So I'm not going into the detail of the solution. Will depend on the solution that we got earlier. That is, if you remember the Lamè's equation was sigma r equal to sigma C1 plus C2 by r square, and sigma was C1 minus sigma 2 by sigma r square. So here, this particular solution may be different, but in this case, it happens to be the right-hand side only. We add to this, so it becomes minus nu 3 plus nu by 8 rho omega square r, and it is added to both. So in this case, the solution becomes sigma r equal to C1 plus C2 by r square minus 3 plus nu by 8 rho omega square r, and sigma theta is equal to C1 minus C2 by r square minus 1 plus 3 nu by 8 rho omega square r square. So these are the solutions for the rotating disk, where the equation of equilibrium is slightly modified. So we can in a way call this modified Lamè's equation, because Lamè's equation doesn't have this part. Okay, so equation 3 and 4 are the solutions of the equation of equilibrium for rotating disk shown in equation 2. Okay, so this is the equation that we have to solve for a particular case. So now we need to put the boundary condition. If you remember, for thick cylinder, we had an internal pressure and an external pressure. So we said at R equal to Ri, that is at the internal radius, sigma R was minus Pi, and at the external radius, R equal to R naught, sigma R was minus PO, outside pressure. But here, if you think of a rotating disk, it has no pressure inside or outside. Outside may be the pressure, that is the ambient pressure. That is also inside, so we ignore that. So at the boundary condition here will be sigma R will be 0 at both R equal to Ri and R equal to R naught, Ro. So I hope you understand this. This is very simple. This is your rotating disk with the inside is Ri, outside is Ro. There is no pressure as such, either in the inside radius or on the outside radius. And since there is no pressure, there is no radial stress at the boundary. So the boundary condition is sigma R is 0 at R equal to Ri and at R equal to R naught or Ro. Now these are very simple algebraic manipulation. So now to do it here, but I show you the results. If you put this condition in equation 3, 4, say if you put R equal to Ri, then sigma R will be 0. And if you put R equal to Ro, then sigma is also equal to 0. So you have got two equations, and from these two equations, from equation T itself, you can get two equations at R equal to Ri and at R equal to Ro. Then you can find out C1 and C2. So C1 uh, works out to be 3 plus mu by 8 Ri square plus Ro square rho omega square. This is very simple. I am not going to do step by step. If you look at it, you will see it will come out very easily. Okay, I repeat. We have got two conditions at R equal to Ri, sigma R is 0, and at R equal to Ro, sigma R is 0. So you have got two equations for the two boundary conditions from equation 3 itself. So if you do that, if you work it out, you get the two constants C1 and C2, and they will count to be C1 equal to 3 plus mu by 8 R1 Ri square plus Ro square rho omega square, and C2 equal to minus 3 plus mu by 8 Ri square Ro square rho omega square. Okay, so you take it for granted for the time being, and you work it out in your leisure time. You will find out that it is very easy to get it. Okay, so with this we go back to equation 3 and 4, 3 particularly, and substitute the value of C1 and C2. Again, this is a very simple algebraic manipulation, and I'm sure you can do it yourself. And you find out that sigma R works out to be 3 plus mu by 8 rho omega square Ri square plus, this plus has come down, plus Ro square minus Ri R naught by R whole square minus R square. This is what you get for sigma R. Let me repeat, sigma R will be 3 plus mu by 8 rho omega square Ri square plus Ro square minus Ri R naught Ro by R whole square minus R square. Now, and if you put this in equation 1, you will get the value of sigma theta. And or you get it from equation 4 itself. You put the values of C1 and C2 in equation 4, you will get sigma theta. And sigma theta comes out similarly, 3 plus mu by 8 rho omega square Ri square plus Ro square plus here it is plus Ri R naught by R whole square minus 1 plus 3 mu by 3 plus mu R square. This is simple manipulation. You can do it and you'll get it. But what is important to understand, how the stress distribution works out within the thickness, because this is the inner radius and this is the outer radius. So we need to know how the stress is varying. Let's take sigma R. Again, I show the variation on the horizontal axis. That does not mean it's only in the horizontal axis. At any distance, or any radial plane, it will be like this. The variation of stress is there throughout anything. So let's see how it varies. If we put R equal to Ri, what happens? You put Ri square and your 1 R square cancels out, and Ri here, Ri and I cancels out. You've got R no, Ro square minus and Ro square. So this becomes 0. So at R equal to Ri, that is the inner radius, sigma R is 0. Clear? At R equal to Ri, this Ri, we put Ri here, Ri, this Ri cancels with this Ri, and if you put Ri here, this I and this Ri cancels out, you got Ro square, so this Ro square and this Ro square cancel out, and you have got nothing, you have got sigma R is 0. Fair enough? So the stress starts from 0. Then if you put R equal to Ro, what happens? You have got Ro square here minus and R square here plus. So that cancels out. You put Ro here, this Ro will cancel out, and you have got Ri square minus, and you have got Ri square. Then again the whole thing cancels out, and you are left with 0. So at both the ends, sigma R is 0. And then it must vary parabolically because you've got a square here, R square. The variable is R. So, of course, one R is also there. So it is not a pure parabola, but it will be something, some variation like this. If you look at sigma theta, you have got a similar picture. If you put R equal to Ri, then this Ri and this Ri and this Ri, this becomes 0. So you've got you don't get 0 here. You've got some magnitude, and it starts with some value here. And then you put R equal to Ro. Similarly, you put some value here. So you got a variation with some magnitude at Ri and some magnitude at Ro. Okay, so you get some approximate idea of how the stress varies. It's quite clear that the sigma theta is not 0 at both ends, but sigma R is 0 at both ends, and it varies parabolically or some such variation, because you have got one R here also in addition to R square here. And here you will not have 0 at both ends, so some such variation. So this is a typical approximate picture of stress variation. So with this, we understand that the stresses in rotating cylinder have got this kind of variation, and we can see that radial stress is 0 at both ends, but circumferential stresses are not 0 at both ends. Now, in addition to this, one important thing we must try to do is what is the maximum stress. In fact, in design, this is the most important point. We must understand what is the maximum stress, because we must check that the maximum stress does not exceed the yield stress. If it does, then there is a chance of failure. So we must find out the maximum stress. Now, what is the maximum radial stress? So the simple thing to do is to differentiate this and equate it to 0. And that's what we have done here. And if you do it here, a simple integration. You see, these are all constants. Only this one and this one are variable. This one is 1 by R square, and this is R square. So this will be minus 2 there was 1 minus so plus 2r cube into some constant minus 2r. So r will be root over ri r naught, ri ro. Okay, so if you differentiate this, you will get r equal to ri ro to the power half or root of ri ro. And if you put it here, put it back in this equation, you will simply get a equation of this sort, ri square plus ro square minus 2 ri r naught. Okay, it will come out here. If you put r equal to root ri ro, you will get this. What is this? This is nothing but 3 plus mu by 8 rho omega square ri minus ro whole square. Okay, so this is the maximum radial value, maximum value of the radial stress. So this is value you get here, and knowing this, you can find out what is the stress you can apply so that the disk does not yield, and there your choice of internal and external radial can be made depending on the stress. Of course, there are many other parameters, but radius is one very important in design. And in material choice, you can have a value of rho and nu, and you have to limit your omega so that sigma does not exceed the yield stress. So this gives you a very good design criteria so that the disk material does not fail at a certain speed and in a certain geometry. We can do the same thing with sigma theta. In fact, in many cases, circumferential stress is more important than radial stress. Circumferential stress is more important than radial stress. And there, we have to find out what is the maximum value of it. Now let's look at a circumferential stress. It's very easy to find out what is the maximum value. The maximum value will be where negative value is minimum, isn't it? If the negative value is minimum, then sigma theta will be maximum. And when is negative value minimum? At r equal to ri. Okay? So we say that sigma theta is maximum at r equal to ri. That's what we have got here. It is slowly coming down here. Great. I'll repeat it again here. We are trying to find out when is sigma theta maximum. Instead of differentiating, there is a simple way of finding it out. Look at this equation. Everything is a positive sign, except that the last term. So if the last term is minimum, then the whole is maximum. When is the last term maximum minimum? When r is ri. R varies between ri to ro. So when r is ri, then sigma theta will be maximum. So the simple thing is that maximum circumferential stress of sigma theta occurs when r is ri. And we substitute that here. We substitute that here in this equation. Very simple to do that. Put r equal to ri here and put r equal to ri here. So you've got 3 plus nu by 8 rho omega square Ri square plus Ro square plus if you put Ri here, this cancels out. You have got another Ro square and then minus 1 plus 3 nu by 3 plus nu Ri square. And if you do simple manipulation, you will get a nice form that sigma theta is rho omega square less 3 plus nu by 8 cancel rho omega square within bracket 3 plus nu Ro square plus within bracket 1 minus nu Ri square. So this is the form of the sigma theta when it is maximum. So I should have written sigma theta maximum here. So this is the maximum value of sigma theta. And here again, it gives you a design criteria, what kind of value of R inside and outside this you can fix, and what kind of material you can take, and what kind of speed you can take to contain that the sigma theta does not exceed the yield state. So using both this equation, sigma R maximum and sigma theta maximum, you can design the rotating disk for its material and its geometry. Yeah, these are the two main things. Now, another important issue is that in rotating disk, suppose we take a solid disk. Now, I think you can well ask, how can a solid disk rotate if you don't have a shaft within? The answer is there are many uses of solid rotating disk within different field forces, which you can have a rotating disk with a magnetic field or electrostatic. There are many cases and many examples of this. So let's look at the stresses when the disk is solid. What does it mean disk is solid? Solid disk means Ri is 0. So let's go back to these two equations and we put Ri equal to 0. So the first term is 0 and the third term is 0. So we are left with Ro square minus R square. So sigma R becomes 3 plus nu by 8 rho omega square Ro square minus R square. And similarly, if you look at this equation, put Ri equal to 0 and put R equal to Ri rather, and you will get a form of the equation like this: 3 plus nu by 8 rho omega square Ro square minus 1 plus 3 nu 3 plus nu rho square by R square. It's simple to understand because what all we are doing is we are putting Ri 0. Ri 0 means first term is 0 and third term is 0. So you are left with Ro square minus this term. Like in sigma R case, we are left with Ro square minus R square. Here, with R square, there is a constant. So sigma theta becomes 3 plus nu by 8 rho omega square Ro square minus 1 plus 3 nu by 3 plus nu R square. So these are the two equations that are needed to find out the stress distribution on a solid disk. Now it's very simple to understand where is the stress maximum. Of course, stress is maximum at R equal to 0. Why? Because you can say sigma R. This is a negative value. So when the negative value is 0 or minimum, then sigma r will be maximum. So let's r 0. Then sigma r is maximum. So maximum value of sigma r is 3 plus mu by 8 rho omega square r o square, because r square is not there. Similarly, sigma theta, we put r equal to 0, and we have got the same equation. So both sigma r maximum and sigma theta maximum are equal to 3 plus mu by 8 rho omega square r o square. Okay. Now, this is the maximum value at the center. Now, let's approach it a different way. Let's put Ri approaching 0 in equation 6. When Ri approaches 0, then what happens? What happens when Ri approaches 0? Instead of making it going to the next equation, if you put here Ri approaching 0, then you have got We've got 3 plus mu by 4 rho omega square r square. So it is 3 plus mu by 4, and here it was 3 plus mu by 8. So there is a factor of 2. So this simply means that if you maximum stress for a solid disk is 3 plus mu by 8 rho omega square r square. But if you cut it in a different way, you have a hollow disk, disk with an internal radius and external radius, but you let the internal radius approach to 0. Then you see that the maximum value of sigma theta, that is this maximum value of sigma theta, that is on equation 6. If you let Ri approach to 0, then what you have? You have 3 plus mu by 4 omega square. Okay. Ri approaching 0. This one is 0. This one is 0. Okay. So you've got 2r square, and this 2r square cancels out. Okay. So we've got 3 plus mu by 4 rho omega square r square. If you take the maximum value of sigma theta. So this simply means that if you have a solid disk, then the maximum pressure at the center is 3 mu by 8 rho omega square r square. But if you drill a small hole, approaching 0 means you have a small hole. Then the radius and then the stress becomes twice. With a hole, there will be a stress concentration, and this will increase stress. And here in this case, it will increase it by 2. So this difference has to be noted, because in general, if we want to rotate a solid disk, we need a whatever a small shaft. Even if it is a very small shaft, a small hole has to be drilled. And with that small hole, this circumferential stress will rise by a factor of 2. And hence, um, we need to consider that if we drill a hole or don't drill a hole. Okay, so that much for today, and we'll do problems on this in the next class. Okay, that's it.